All right, let's dive into some seawater here and try and figure out what the hydronium concentration is in this seawater. So here for number one, we are given the concentration of hydroxide, and that is 2 times 10 to the negative sixth molar, and we're being asked to calculate what the hydronium concentration is. So very simply here, we've just got this equation, the Kw equation. So the hydronium concentration times the hydroxide concentration gives us Kw. So if we wanted to solve for the the hydronium concentration, then what we would need to do is the following. We just divide both sides by the OH concentration, and we would get the equation like this. So now, Kw is 1 times 10 to the negative 14th. We want to divide that by 2 times 10 to the negative 6th. So that's the concentration of hydroxide, and that gives us the concentration of H3O plus, which would be 5 times 10 to the negative 9th molar. All right, so the correct answer for number one is C. Now moving right along to number two, based on the answer from problem one, what is the pH of the seawater solution? So we got to remember here that pH is the negative log of the hydronium concentration. Okay, all that the P represents here is negative log, right? So if we're taking the negative log of the hydronium concentration, we're getting pH. So just to remind you real quick that if we had a POH here, then we'd be taking the negative log of the hydroxide concentration, the OH minus concentration. Okay, so all that the P means is negative log, and then what's inside the negative log, what we're taking the negative log of, is represented here by either the H or the OH, meaning the hydronium or the hydroxide concentration. So here with pH, we're looking for hydronium concentration, the negative log of the hydronium concentration, which we found here in number one. So all we need to do to find the pH is to take the negative log of the concentration we found in number one. And when we do that, we find that the pH of the saltwater is 8.3. A patient enters the ER, and it is determined that the concentration of H3O plus, the hydronium, in their blood is 4.46 times 10 to the negative 7th molar. What is the pH of their blood? So once again here we're finding the pH, so we can just use this equation that we used in number two. So where pH is the negative log of the hydronium concentration. Okay, got to be careful to make sure this is hydronium, and it is. So when we take the negative log of 4.46 times 10 to the negative 7th, the answer that we get is 6.35. And so 6.35 is the pH, and that is what we're looking for. So we're good. And that corresponds to C, so C is the correct answer for number three. The optimum pH for a swimming pool is 7.4 because it matches the pH of the human eye. If the pH differs by more than 0.1 or 0.2 pH units, the water may cause eye irritation. If you go swimming in the IU Student Rec Center pool and the concentration of OH minus here is 1.05 times 10 to the negative 6th molar, will your eyes hurt afterwards? And what is the pH of the water? So I think that the quickest approach to this question is simply to take the hydroxide concentration and figure out what the pH is. So I was being very specific here in number three about making sure that we're taking the negative log of the hydronium concentration. You go, well, that's kind of obvious, right? Well, here it's not so obvious, because if you just went along and said, oh, okay, I have a molarity, I just take the negative log of that and I'm done, what you would find is the POH. So if you took the negative log of this concentration, you would find the POH. And that's not quite what we want, but we can use it to get us to the pH. So let's go ahead and begin by doing this. So I can show you two different ways to do this. First of all, let's go ahead and take the negative log of this. Here's method number one. So the negative log of the hydroxide concentration is going to give us the POH. Okay, we have to be very careful here of what we're taking the negative log of. We're taking the negative log of the hydroxide concentration, and doing that will give us the POH. Okay, not the pH, the POH. All right, so then the next thing we would do is we would say, okay, well, from this equation, 14 is pH plus POH. Okay, we can solve for the pH. So pH now equals 14 minus POH. And right here, our POH we already found. That's just the negative log of this concentration. So we take that, and we plug it into here, and go 14 minus that number, and that's going to be our pH. And then, of course, we'll know whether our eyes will experience irritation, because we can then evaluate whether it's 0.1 or 0.2 pH units above or below 7.4. So let's go ahead and do this numerically now. So the POH, here, let me write it like this, POH equals, we'll just round like this, 5.98. All right, so if we know the POH, now we can solve for the pH. So that means that pH is going to be 14 minus 5.98. And so that gives us a pH equals 8.02. Okay. So here's method number one. This is one way you can do it. Another way you can do it is like this. Here's method number two. Both ways will get you to the same answer, and we'll see this in a second. Remember the Kw equation? Kw equals the hydronium concentration plus the hydroxide concentration. Well, we can use this because we are given the hydroxide concentration. So if we take this and plug it into this Kw equation right here, then we can solve for the hydronium concentration. So just the same way that we did in number one. So we'll just go ahead and do H3O plus equals Kw divided by the OH minus concentration. Okay, and we're given the OH minus concentration, so I'll just come down here and say 1 times 10 to the negative 14th divided by the OH minus concentration, that's this, 1.05 times 10 to the negative 6th molar, gives us 9.52 times 10 to the negative 9th molar H3O plus. Okay, so this is now our concentration of H3O plus, hydronium. So if we take the negative log of this, so we take the negative log of our answer here, so we take the negative log of H3O plus, that will then give us the pH by definition, right? And when we do that, we take the negative log of this number, that gives us 8.02. So you can do it either way, whichever way you're more comfortable with, and here we can see that either way gives you the same answer, 8.02. A is the only one that has 8.02 as part of its answer, but let's just go through all the motions and make sure that we answer everything totally correctly. A suggests that yes, our eyes will burn, and so can we confirm that that's true given the pH? Yep, absolutely, because here this is about 0.6 pH units away from 7.4. So it is indeed more than 0.1 or 0.2 pH units different than 7.4, so indeed our eyes will burn. So A is the correct answer for number 4. In number 5, if a dilute solution of HCl is prepared by mixing pure concentrated HCl with water to give a final concentration of 0.1 molar HCl, what is the concentration of H3O plus in this solution? So the key thing here to note is that HCl is a strong acid. This is a very important clue. So when you dump HCl into water, this is what happens, right? You make hydronium and chloride. Okay, and the HCl will completely split up. So what you will see here is a 1-to-1 mole ratio of HCl to hydronium. So for every 1 mole of HCl, there is 1 mole of H3O+. So 1 mole of H3O+ is made. Let me make a little side note here that this is not always 1-to-1. So if you have something like H2SO4 in water, making H3O+ and sulfate. Okay, let me make sure that's all in the picture here. So you're making hydronium and sulfate. What you have to be mindful of is that there's 2 protons here. Okay, so when sulfuric acid completely electrolytically dissociates, there's going to be 2 protons for every 1 sulfuric acid molecule. So there must be a 2 here in order to make this equation balanced. Okay? So now in this situation, 1 mole of H2SO4 is going to produce 2 moles of H3O+. Okay? So just be mindful of how many protons are coming off of the strong acid. And that will tell you the mole-to-mole ratio, just in case it's not a monoprotic acid like HCl is. But in this case, it's a little bit simplified for us because it is indeed a monoprotic acid, so it is a 1-to-1 mole ratio. So when 1 mole of HCl splits up, you make a mole of hydronium. So how do we use this relationship now to figure out what the concentration of hydronium is? Well, this is where we come in. This is where the concentration comes in, and we can then apply this mole-to-mole ratio to the concentration. And here's how. Remember that molarity is moles per liter. Okay, this is going to be a very important definition. Because now we're going to say, okay, well, to say that we have 0.10 molar HCl means we're saying that we have, I'm going to come down here and write it here, 0.10 moles of HCl in a liter of solution. Okay, so if I had a liter of this stuff, I would have 0.1 moles of hydrochloric acid. Now, why don't we just go ahead and apply this mole-to-mole ratio? And say if we want to figure out what the concentration or molarity is of the H3O+, let's convert this into the H3O+ molarity using the mole-to-mole ratio, like this. Okay, so this right here is going to comes from the balanced equation. Okay, that's this one right here. So now our moles of HCl cancel, and lo and behold, we have moles of H3O+ per liter. And anytime you get moles per liter, that is a molarity. So what we see here is that the final molarity of the H3O+ is the same number, because this was just a 1-to-1 mole ratio. So it's 0.1 molar moles per liter H3O+. So what we've done here is we have changed the units from HCl to H3O+. That's the power of units. That's why I keep encouraging my students and everybody in the chemistry classes to write down units. They are super, super important because sometimes you don't change the numbers. But the numbers have meanings, right? So this one represents moles of hydronium. This one here represents moles of HCl. If you didn't show your units there, then the numbers wouldn't have any meaning. So you want to always make sure you show your units, so that way you can mathematically justify canceling out moles of HCl and converting into moles of H3O+ per liter. So it's very important to start showing units if you haven't been showing them, because stuff like this becomes much easier if you can show your units canceling out and becoming moles of hydronium per liter. Okay, so there's my my shameless plug for units once again. And you'll probably hear that a lot throughout the semester because stuff is going to get tougher, and it's going to be made a lot easier if you are showing your units. So units, 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 really super important. So this is a quick and easy way to figure out what the concentration of hydronium is if you're given the HCl concentration. Let me make one final note here. If this was sulfuric acid, so if we had a situation like what I showed here where we got H2SO4 electrolytically dissociating and interacting with the water to make 2 hydroniums, then what you would do here is you would say that this is a 2 to 1 mole ratio. Okay, if this was 0.1 molar H2SO4, then you'd have 2 moles of protons or hydroniums for every 1 mole of H2SO4. And so doing that would give you 0.2 molar H3O+. So that's what you should expect to see if you have a diprotic acid like sulfuric acid. And of course, if you had something triprotic, you very easily could also put a 3 right here. That represents that for every 1 mole of acid, 3 moles of protons have to come off of that acid. Okay, so that's how those kinds of problems will work. So with 0.1 molar, A is the correct answer for number 5. So here for number 6, I kind of have already foreshadowed this idea of having multiple protons with acids. We can also have a similar situation with bases, because bases don't necessarily have to have 1 hydroxide on there. This one, strontium hydroxide, has 2. Okay, so let's be clear here that when strontium hydroxide dissociates, strontium hydroxide, got to remember that's one of your strong bases, right? Strontium hydroxide is going to make Sr2+, it's aqueous of course, and 2 hydroxides. Okay, that's what this 2 represents. So for every mole of strontium hydroxide, when it completely dissociates, it's going to make a mole of strontium ions and 2 moles of OH-, of hydroxide ions. That's very important because now it's no longer a 1-to-1 mole ratio. If we wanted to figure out how many moles of hydroxide are made, we have to say, okay, well, for every 1 mole of strontium hydroxide, there are 2 moles of hydroxide ions that come out of this electrolytic dissociation. Okay, so now we're ready to do exactly the same thing that we did with the acid, except these are hydroxide ions. So if we're looking for the pH, then what we want to make sure we keep in mind is that when we take the negative log of our concentration, which is going to be double this, and I'll show you that in a second, what we're finding is the POH. So it's the POH that we're finding. These, when this dissolves, the strontium hydroxide at this concentration dissolves, so 1 times 10 to the negative 3rd molar, I'll go moles per liter, and this is moles of strontium hydroxide. When this many moles of strontium hydroxide dissolve, we're going to make twice as many moles of hydroxide ions. Okay, so we're going to get 2 times 10 to the negative 3rd molar, I'll just go molar, hydroxide. If you just took the negative log of this number up here, or if you just took the negative log of this number here, you would have not gotten the correct answer, because this question is specifically asking for pH, which is the negative log of H3O+, not of OH-. So the first thing you had to do is you had to identify that strontium hydroxide is a strong base, and it electrolytically dissociates into 2 hydroxides for every 1 strontium hydroxide, just by this equation. So there's your mole to mole ratio. And then the second thing you could do is recognize that what you get out of this is the hydroxide concentration in the solution, okay, not the hydronium. So let's go ahead and take this now and see if we can use it to figure out what the pH actually is. Right, let me bring you up a little bit like this. If we went ahead and took the negative log of the hydroxide concentration, that gives us the POH, right? That gives us the POH. So let me go ahead and do that. A negative log of 2 times 10 to the negative third gives me a POH of 2 point, we'll say 2 point, no, I shouldn't round like that. Not yet. I'll go ahead and round it like this, 2.699. That is our POH, not the pH. Okay, in order to figure out what the pH is when the POH is about 2.7, we can employ this equation. Okay, and so now we know what our POH is. That's going to go right here. So let me go ahead and arrange this for pH. pH equals equals 14 minus POH. So it equals 14 minus 2.699. Okay, so 14 minus 2.699 is going to now give us the pH. So the pH of the resulting solution is 11.30. All right, so there's a few things you had to recognize here. First of all, when strontium hydroxide dissociates electrolytically, it makes 2 hydroxide ions. You know that because it's OH2 right there in the equation, or the chemical formula. The next thing you needed to recognize is that this is the concentration of hydroxide ions. We're not making hydroniums here, we're making hydroxides. So when you have this molarity, you can convert it into hydroxide ion molarity, and that's 2 times 10 to the negative third. And when you take the negative log of this value, it gives you the POH, not the pH, the POH. So once you got the POH, then the way I prefer to do it is just to take the pH plus POH equation, solve it for pH, and then plug in the POH, and that gives you 11.3 as your pH. So D is the correct answer for number 6. You can also use the KW equation. I'm not going to go through it here. I'll go ahead and leave that up to you. If you happen to prefer using the KW equation, then you can just plug this number into the KW equation without needing to take the negative log of it. And then that will just give you the hydronium concentration, and then you take the negative log of that, and that'll give you the pH. Both ways will give you the same answer. Doesn't matter which one you do. So you just go ahead and choose by your preference, but always make sure you're careful to take note of what you're taking the negative log of. If you take the negative log of this, you're getting the POH, and then you have to do this process. If you use the KW equation and you solve for the hydronium concentration and you take the negative log of that, don't do this, because when you take the negative log of the hydronium concentration, that already gives you the pH. So the answer that you'll get is already going to be pH, and they both should give you 11.3. And so 11.3, or D, is the correct answer for number 6. For number 7, we're being given a solution of a mixture of nitric acid and sodium hydroxide. We're being asked to determine what the pH of the resulting solution is. So let's go ahead and do this. In order to figure out what the pH is, we would have to know whether we have anything in excess. So do we have hydroniums in excess, or do we have hydroxides in excess? If they are not in excess and we have exactly the same amount of each, then the solution is considered neutral, right? And by being neutral, the pH would be 7. So if that were the case, A would be the correct answer. If we had an excess of acid, then the pH would be less than 7, so that would be B or C. Or then if we had more base, so the hydroxide would be in excess, then D would be the correct answer. So let's figure out which of these is the correct answer. In order to do that, we have to figure out, first of all, how many moles of acid do we have? And then we got to figure out how many moles of base we have. So if we have 10 moles of H, we'll just say H plus, because nitric acid is a strong acid, so it's going to split up into H plus and NO3 minus. So there's 10 moles of H plus in a liter of nitric acid. That's pretty remarkable. That's a lot of hydronium. Okay, and we have 0.05 liters of it. So if we take 10 moles per liter and multiply it by 0.05, we would conclude we have 0.5 moles of H plus. Okay, now let's neutralize it with the base and see if we have any base left over or acid left over, or if they end up neutralizing each other out. So let's go ahead and go like this. Now we have 0.5 moles of OH minus per liter. Okay, and how much base do we have? We have a whole liter of it times 1 liter. So now my liters cancel, right? And so I have a 0.5 moles of OH minus. Interesting. I have the same number of moles of acid as I have of base. Well, like we just got done saying here, that if the number of moles of acid and moles of base are the same, and they neutralize each other out, we're going to get a neutral pH, and that pH is 7. Okay, so this is basically a neutralization reaction where anytime we wanted to figure out how much acid we had in there and we neutralized it with the base, we got the pH up to 7, and that's when we knew we had added the same number of moles of base as there were acid. And here we're doing exactly the same thing. So we've added the same number of moles of base as there was acid, and the two neutralized each other out completely, so there is not an excess of either one, and the pH turns out to be 7. So A is the correct answer for, well, number 7. How convenient. Okay, number 8 says, what is the pH of a solution prepared by diluting 50 milliliters of 0.25 molar HCl to a final volume of 1 liter? So I hope this sounds familiar for you in that we have to employ C1V1 equals C2V2. So our initial concentration and initial volume are known, and C2 is unknown, the final concentration, but we do know the final volume. So C1 is 0.25 molar. V1 is 0.05 liters. So, sorry, this is molar, and that's liters. Now this is going to equal some C2 times a volume, and our volume that we want is 1 liter. So let's go ahead and solve for C2. So I'm just going to go here and say 0.25 times 0.05. So that solves for this. This is 0.0125. And then I just divide it by 1, so I cancel out my liters. And that gives me C2. So C2 is 0.0125 molar HCl. Okay. So just like what we were talking about earlier, HCl is a strong acid, so it completely electrolytically dissociates, splits up into H plus and Cl minus, right? So by completely splitting up into H plus and Cl minus, we know that there's a 1-to-1 mole ratio for that splitting, that dissociation, and so we can convert that molarity from HCl into H plus, or H3O plus if you throw water in there too. It's still a 1-to-1 mole ratio. And it gives us a molarity of 0.0125 molar. Same number, different units of H3O plus. And so now we just can take this molarity and say, okay, what is the negative log of it? The negative log, when we take the negative log of it, will give us the pH. So let me go ahead and do that. The negative log of 0.0125 is going to be 1.9. All right, so 1.9 here is the correct answer for number 8. Now in number 9, we're trying to perform a neutralization, or we've got an acidic industrial waste, and we're trying to neutralize it with a base. So in order to figure out how much base we need to add, we have to figure out how many moles of acid, or hydronium, are in our industrial waste. So how do we do that? Let's start out with the pH. So pH is a way for us to tell, the negative log, what the hydronium concentration is. Okay, and we can start out by identifying that the pH here is 1.3. So if we take the anti-log of the pH and the negative log of the hydronium concentration, what that is it's going like this. This is 10 to the negative pH equals 10 to the log of H3O plus. Okay. Now, because this is log base 10, raising 10 to the power of the log of the hydronium concentration cancels out the log. And so what this does is this provides for us the H3O plus concentration. So let's go ahead and do that. 10 to the power of negative 1.3 gives us a hydronium concentration of 0.0501 molar. Now, let's remember this is moles per liter. So when we have 5 liters of our sample, so we can multiply this by 5 liters times 5, and that tells us that we have 0.25 moles of H3O plus. Okay, we'll make sure that's all in there. All right, so basically a quarter of a mole of H3O plus is what we have. Now remember, when we're trying to neutralize something, what we're doing here is neutralization is we're taking H plus, or hydronium. You can be more specific and include water. I'm going to leave water out for now just for simplicity. Hydronium and hydroxide, or just a proton and hydroxide, are going to react to make water. So if I wanted to take this 0.25 moles of H3O plus and convert it into moles of hydroxide, which is what I really want to know, what I have to do is I have to take this and multiply it by the mole-to-mole ratio of protons to hydroxide. Well, we see that there's 1 mole of protons that is neutralized for every 1 mole of hydroxides we dump in the solution. Okay, certainly something we've seen before. So when we're saying we have I'll just skip down here. When we're saying we have 0.25 moles of H3O plus, and we want to neutralize this H3O plus with hydroxide, we say, okay, well, from this reaction, we know that it's a 1-to-1 mole ratio of hydroxides to hydroniums. So we can apply this mole ratio to this number of moles of hydronium, cancel out the moles of hydronium, and now we are in units of moles of hydroxide. Once again, units changed, numbers didn't change. That's why writing down the units is so important, because you mathematically justify going from moles of hydronium to moles of OH minus. Okay? Once again, I'm a big advocate for units. So you're probably going to be sick and tired of me saying this, but this is where the rubber meets the road, is right here. Because things like this, if you just showed your numbers, not your units, wouldn't make any sense. How do you go from hydronium to hydroxide? But when you show your units like this, you can demonstrate that the units cancel and that they convert into moles of hydroxide. So you now have 0.25 moles of hydroxide. Okay, from moles of hydroxide, we need to still figure out how many moles of sodium hydroxide we need. So let's remember that when sodium hydroxide, because that's the species we're going to use to do the neutralization, so we got to understand how it dissociates. Sodium hydroxide is a strong base, tying everything together, that dissociates in water, right? In water, so all of this is aqueous. dissociates into sodium plus and hydroxide minus, right? So now if I have 0.25 moles of hydroxide, and I want to figure out how much sodium hydroxide that makes, or that requires, I guess you could say, then I just refer to the equation and I find that I need a mole of sodium hydroxide to give me a mole of hydroxide ions. Okay, that's simply because it's a strong base and you dunk it all in there, and that's going to provide for you all of those moles of hydroxide ions, like this. You could also do it with a weak base, but the chemistry gets a little bit more complicated because we have to consider the equilibrium. So here it's very simple because it's a strong base and we can very easily conceptualize this relationship. Moles of hydroxide cancel, and now we're in moles of OH minus. So once again, numbers didn't change, but the units changed. So we go from moles of hydroxide into moles of sodium hydroxide. Okay. So now that we're in moles of sodium hydroxide, the last step is to say, okay, well, how many milliliters do I need, or how many liters do I need? How much volume do I need of this sodium hydroxide solution? So let's remember in the problem here that we have 0.5 molar sodium hydroxide. So immediately I recognize that I have 2 out of the 3 things I need for molarity, out of the molarity equation. Molarity equals moles. I'll go ahead and put moles of sodium hydroxide per liter, right? We have molarity. That from the problem is 0.5. And we have moles of sodium hydroxide that we need. So the last thing that we do is we solve for the liters of sodium hydroxide that deliver 0.25 moles of sodium hydroxide. So let me just plug all those numbers in for you. 0.5 molar. And we want 0.25 moles. And so in order to find what volume we need, we conclude that the volume is 0.501 liters, right? So that corresponds to 501 milliliters, because we just multiply that by 1,000 to convert into liters, or excuse me, milliliters. So B is the correct answer for number 9, 501 milliliters. That was kind of a long one. It was a little bit complicated, but I wanted to show every single step so that nothing is a mystery as to how I went from one thing to the other. All you want to do is just recognize that when you're neutralizing something, you're trying to get the same number of moles of base in there as you have moles of acid. And at that point, you're going to bring the pH to 7, so you're neutralizing the solution. And so if you can just solve for the number of moles of acid, then you can very quickly convert into moles of base. Okay, so this is a very simple example. You can honestly just skip all of these steps, and because everything's one-to-one, and like numerically figure out the volume. And go, oh, okay, 501 milliliters is the only one that has the right answer, so I'll go ahead and pick B. That works for this one, but the reason I showed this is not to bore you out of your mind, but because there's merit in taking every step like this, maybe not on a timed quiz like this, but just for your development of your chemical intuition, because as these problems might get more complicated, you might incorporate a base in there like strontium hydroxide, where we learned from number 6 that strontium hydroxide has more than one hydroxide, right? Or other complications like this. And if you do this entire process like this that we laid out, it's never going to trip you up. You will always get the right answer because you're always considering what the reactions are, what the mole-to-mole ratios are, and multiplying by the appropriate ratios to make sure that you're obtaining the right number of moles of acid and base, so you find where it's the same number of moles of acid and base, and that gets you to the pH of 7, where you neutralize the solution. So I just wanted to be really systematic, so I showed every step, just in case later on you might see something a little bit more complicated that's not all one-to-one, and then you can use this kind of a process to get you the right answer. Okay, so there we go. That was number 9. All right, lastly for number 10. we're almost done with this marathon. How many grams of potassium hydroxide should be dissolved in 200 milliliters of water to yield a solution of pH with a pH of 9.3? Okay, let's forget about grams for a second. Let me just focus on moles. So I want to figure out how many moles of KOH I need, and then I can do all of the grams and converting it into grams off of the periodic table. So I need a pH of 9.3. Well, pH, if I take the antilog of pH, that's going to provide for me the hydronium concentration. That's kind of indirect for me. I like to think in terms of pH plus pOH equals 14. That's a really easy equation for me to remember. So I'm going to go ahead and use that one. You could also use the KW equation, just like in all the previous questions. They'll both give you the same answer. But I'm going to show pH plus pOH in this one because it's a little bit easier for me and hopefully appeals to a lot of other people. So my pH is 9.3. or 9.30 to be technical. And I know that my pH plus pOH equals 14. So I have a relationship. I have a way to figure out what the pOH is. The pOH is simply 14 minus the pH. And that gives me the pOH. Why do I care about the pOH? I care about the pOH because the pOH is the negative log of the hydroxide concentration, right? Just by definition. So if I find the hydroxide concentration, then I can figure out how much KOH I need. Because KOH is a strong base, it's going to give us hydroxides. I can figure out how much KOH I need in order to give me the concentration I'm looking for. So let's go ahead and do this numerically. 14 minus 9.3 is going to give me a pOH of 4.7. So my pOH is 4.7. Now, if I want to figure out what the hydroxide concentration is, I need to take the antilog. So let me go ahead and do this. 10 to the negative 4.7 equals 10 to the log of the hydroxide concentration. And remember, log is base 10, so when I take 10 and raise it to this power, it cancels out my log. So it leaves me with just the hydroxide concentration. So 10 to the power of negative 4.7 is going to give me basically 2 times 10 to the negative fifth. My calculator says 1.995. You might get something similar to that. I think that just rounding it up to 2 is perfectly okay. So this now gives us the hydroxide concentration. So this is moles of hydroxide per liter of solution. All right, units, 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 really super important. So you know what you're talking about, what your numbers mean. So I have a way to relate moles of OH minus to the volume. So when I have a liter of this solution, I have 2 times 10 to the negative fifth moles of OH minus. Okay. When we electrolytically dissociate KOH in water, it's going to make K plus and OH minus, just like the sodium hydroxide, right? Because it's a strong base, it's going to give off hydroxides. So that's all hopefully familiar to us at this point. So we have a 1:1 mole ratio of KOH to hydroxides, right? So now if I just take this, 2 times 10 to the negative fifth moles of OH minus per liter, and say how much KOH do I need to add into the solution in order to give me this many moles of OH minus, you just say, oh, I just look at the mole to mole ratio. I need 1 mole of KOH for every 1 mole of hydroxide. Moles of hydroxide cancel, and I am in moles of KOH per liter of solution. So once again, numbers didn't change, but units did. Okay, So now we have 2 times 10 to the negative fifth moles of KOH. Are we done? Well, not quite. We're not quite done. The last piece of information is that this is per liter. Sorry, I forgot to put that in there. Moles of KOH per liter. Do we have a liter? No, we don't. We want to make, let me go back up here, we want to make 200 milliliters. Okay, so we don't want a whole liter. That would be wasteful. We only want 200 milliliters. So what do we have to do? We have to just take this and say, okay, this is how many moles I have if I have a liter, but if I only have 200 milliliters, or 0.2 liters, then I just multiply it like this. My liters cancel, and now I get moles of KOH that I need for 200 milliliters. So I'm going to take this and just multiply it by 0.2. And so down here I have now 4 times 10 to the negative sixth, really small number, moles of KOH. That's how many moles of KOH I need in order to make 200 milliliters of this solution. Well, we're almost there. We're very, very close. The last thing that we need to determine is how many grams 4 times 10 to the negative sixth moles of KOH weighs. In order to do that, we need to just consult the periodic table with the molar mass and multiply those together. It's going to look like this, times 56.1 grams of KOH per mole of KOH. Now moles of KOH cancel, and we are in units of grams of KOH. So if I just do this real quick, 4 times 10 to the negative sixth times 56.1 grams per mole, I get 2.2 times 10 to the negative fourth grams. Okay, and if you just take this and say that there's 1,000 milligrams in a gram, grams cancel, and you get 0.22 milligrams. Get that all in there. There we go. 0.22 milligrams of KOH. And so that is how you would do number 10. And with 0.22 milligrams as our answer, B then is the correct answer for number 10. And that was the quiz.